So the second section of this chapter, 8.2, is called the free energy change of a reaction, tells us whether or not the reaction occurs spontaneously. So last section we talked about what it means for something to occur spontaneously, that we don't need to put in energy, that it will eventually just happen on its own, but whether or not it's going to take millions of years, it'll eventually happen on its own. But these equations or these reactions that occur spontaneously will increase the entropy of the universe, meaning the disorder of the universe. The reason why this matters to us is that biologists want to study this to know how this is happening inside your body. So which reactions are we putting energy into, and which ones are happening on their own, and which ones are releasing energy, etc., etc. And so in order to do this, we have to know about the changes that happen in chemical reactions. So we're going to talk this entire section about something called free energy. And if you ever see the letter capital G, it means free energy. And if you ever see that delta next to it, that triangle, this triangle right here, means change. So delta G means change in free energy. And the term free energy means energy that is available to do work when conditions and when temperature and pressure conditions are uniform. So for all intents and purposes that we'll be talking about, energy that's free to do work. Sorry. So that's what delta G is. And so the change in free energy, delta G, during a process is related to the change in a couple of things. So we have an equation here. So we have delta G equals delta S minus delta G equals delta H minus T delta S. So there's a lot of factors going into the change in the free energy. So delta G, remember, means free energy, the energy available to do work. Delta H is the change in total energy, and that's enthalpy. So this is total energy, not just energy available to do work. T is temperature in units that we call Kelvin. You won't need to worry much about that, but no, it's not Celsius or Fahrenheit. It's in something else called Kelvin. And delta S is change in entropy. So now we have enthalpy and entropy. Entropy is disorder in the universe, and enthalpy is total energy. So try and keep those straight. So delta G is a consequence of the change in overall energy, delta H, minus the change in the temperature times the temperature times the change in the entropy, so T delta S. And so processes that occur spontaneously will have a negative delta G, meaning that as the process happens, energy is lost. And spontaneous processes release energy, so they have a negative delta G, and this energy can be used to do other jobs, to perform work. So again, free energy is a measure of a system's instability, its tendency to change to a more stable state. So if a system has a lot of free energy, that means that it's likely to change because it's likely to release that energy for a process to happen spontaneously and to release its energy to outside of the system in order to change into a more stable state. So if we change the system into a more stable state, we're increasing the entropy of everything around it because we just created disorder around it. And during a spontaneous change, free energy decreases and the stability of a system increases. So as we, I'll get to an example later. So as we go from a disordered molecule, we're going to spontaneously change into a more ordered molecule. So the stability changes, the stability, not the order. We're becoming more stable, but we have less energy. So equilibrium is a state of max stability. So that means that we are as stable as we're ever going to get. And a process is spontaneous and can perform work only when it's moving towards equilibrium. So it's always working to reach this maximum stability, and that's why these things are spontaneous. So if you're already at equilibrium, you're not going to happen spontaneously because there's no place further to go. You're already at equilibrium. So, for example, these are some stable versus non-stable states. So up here at the top of the diving board, you're not very stable, right? You could fall at any moment. But you have a lot of free energy because you have a lot of energy. You have a lot of potential energy because you're at the top of the diving board. So you're more free energy, more G. You're less stable, but you have a lot more capability to do work, a lot more capability to move, right? It's really easy to fall off a diving board. And so as we change states, as we change from top of the diving board to in the water, now we have lower free energy. We're more stable. We're not going to fall from the water into something else, so we're more stable. But we have less capability to do work, right? We can't fall anywhere right now because we're already at the lowest energy state. And we have less free energy. We have less energy just available to do work. And that was a spontaneous change. So we see the free energy of the system decrease because we had high free energy up here and low free energy down here. The system becomes more stable. We're way more stable in the water than we are on top of a diving board. Sorry. And we release that energy to do work. So the work there was moving from the top to the bottom. Diffusion is an example of a spontaneous process. So here we have a lot of free energy, but we're less stable, right? So what that means is as diffusion happens and these molecules spread out, it's so much easier to maintain this than it is to maintain that. Since molecules are always moving, it's way more easy to maintain them spread out than them together. So that's why it's more stable down here. And there's greater work capacity. Work here meaning moving around. So it's way easier for them to spread out here than it is down here because they're already spread out. Same thing right here. This molecule is glucose right here. And so as we break down glucose into carbon dioxide and water, this is far more stable. You're not going to break down carbon dioxide. You're not going to break down water. So it's way more stable, but there's way less energy available to do work. In glucose, there's tons of energy available to do work. That's what powers every single process inside your body, is the energy harnessed from glucose. So just think about each of these things. These are far less stable, and these are far more stable down here. And so we can talk about these in terms of the reactions that happen inside of our bodies in two different ways. So we have exergonic reactions and endergonic reactions. So exergonic reactions are those that release energy. So remember, we're releasing energy. We are increasing the entropy of the universe. So these things are spontaneous. Endergonic reactions absorb energy. Okay, so they take in energy from their surroundings. They're not spontaneous. And since we need to put in energy to them, they decrease the entropy of the universe. So they're not going to happen on their own because they are, unless someone gives them energy, it's never going to happen. Okay, so here are the graphs to talk about these two things. So this is a exergonic reaction. So over here we have the amount of free energy on the y-axis, and here's as the process moves forward. So the reactants right here, what we have before the reaction, have far more free energy. They have way more capability to do work, so they have a much higher level of free energy. And the products down here have much less energy, free energy, energy available to do work. They have far less. So this much energy was released. So delta G is greater than 0. The change, or is less than 0. I'm sorry, the change in energy, all of this right here, this is our delta G. So this is an exergonic reaction because all of this energy is released. And the reason that it's negative is because these products down here have far less energy than right here. So we have negative energy at the end. It's different than endergonic reactions, which are the exact opposite. So we start off with our reactants, what we start with at the beginning of the process, having far less energy than what we end with. So for this process to happen, we have to put in all of this energy right here, okay? This energy is required for the process to happen. But at the end, the products are now storing this energy. So we went from something that didn't have very much energy, something that was probably a little bit more stable, to something that is less stable because it has more energy, okay? So delta G is positive here because we put in all that energy. And that is an endergonic reaction. This is not spontaneous because it can't happen unless we put in all this energy right here. And I'm going to stop right there for this section.